Okay, but like I said, we are talking about stoichiometry today. And so we need to remember how to use chemical equations. And so we're really going to be focusing on the coefficients or the numbers in front of our species here. And so what these coefficients represent is we can think of ratios. And so they tell us the ratio of the number of molecules. So this means our ratio of N2 is 1 to 3 H2 to 2 ammonia. So this is if we were to do this reaction with 1 N2 molecule, we'd need 3 H2 molecules to make 2 NH3s. So just like you would make a recipe for pancakes, maybe it takes 2 eggs plus a cup of flour equals 4 pancakes. So it's just a ratio of the parts that we need to make our products. And so this can be used for the number of moles. So we learned that new unit, the mole. You can use the coefficients and ratios to compare moles to moles. And so the ratio for the number of moles, we have 1 mole of N2 for 3 moles of H2 and 2 moles of NH3. What about grams though? Can we just use the coefficient for the number of grams we have? No. So we have to use the periodic table. If you guys were to look up N2, 1 nitrogen is 14 times 2 is 28. So 1 mole of N2 weighs 28 grams. This is in ratio to 3 H2s. And so the mass of 1 hydrogen is just 1. So it'd be 6 grams. And then NH3, which nitrogen is 14 plus 3 is 17. We have 2 of them, which gives us 34 grams. So now the question below asks, does 1 mole of nitrogen weigh the same as 1 mole of hydrogen? No, it doesn't. If you think about the whole periodic table, each element has a different mass because that's how much they weigh per mole. Where did we get the values from for masses? Periodic table. I'm just going to abbreviate that as PT. Now, wasn't our mass ratio, is that the same values as our mole ratio? No, they're completely different. So we need to make sure that we know that we can use the coefficients for moles and molecules, but we can't use them for mass. But what, just talking a little bit more about mass here, what's the mass of both the reactants added together? 34 grams. And what's the mass of the product? 34 grams. What does this show us? The law of what? Conservation. Beautiful. So pretty neat. That means our equation is balanced. All right. We're just going to get right into it. I, again, think you guys will enjoy mole to mole ratios here. So the first question is asking, what is the molecule ratio of these? Well, what's the number in front of O3, even though it's not there? 1. So our ratio of molecules is for every O3, there's 1, there's 3 NOs, and 3 NO2. So we're just using the coefficients to talk about the ratio of each of these species to each other. Now, if there is 1 O3, this will work. Oh, my pointer's not working. If there's 1 O3, and that gives us 3 NO2s, so the ratio is 1 to 3. What if we have 25 molecules of O3 then? Exactly. Then we'd have 75 NO2. So just how you would use a ratio, you can use it as a multiple. So if we have 25 molecules of O3, we have to have 3 times as many NO2s. So that would give us 75 molecules NO2. Now I'm going to show you guys how to use conversion fractions. So we're not away from those. We're doing lots of conversions with student. These ones are too bad though, when we're comparing moles to moles or molecules to molecules. So here, if you notice, we're going from molecules to molecules. If you see this, we only have to use coefficients because we can get at molecules from the coefficients. So we always start with what we know. That has not changed. So we're going to write down the value given. Well, we were told we have 1.81 times 10 to the 24th molecules of NO. We're going to get ready for our conversion fraction. So we are going to multiply by a fraction. And since we are going molecules to molecules, we're using a molar ratio. And so now we're going to get to use our coefficients here, but we have to make sure we cancel out molecules of NO. We don't want that unit anymore. So I'm putting that on the bottom. So now that molecules of NO here will cancel with the one here. And our target is molecules of NO3. Or O3, sorry, not NO3, O3. Now, the values we give both of these, just the coefficients. So what's the number in front of O3 from the equation? So you put a 1 in front of molecule O3, and then NO gets a 3. So really, we're just multiplying this number by 1/3 for the molar ratio. Put that in your calculator, and you would get 6.0 times 10 to the 23rd molecules O3. That would be your answer. Now, if we simplify it a little bit, let's just work with a whole number here, because this is probably a little bit more what you'll see. So it's asking how many moles of O3 are needed to react with 3 moles of NO. So we start with the value given, 3 moles NO. Get ready for a conversion. But since we are going from moles to moles, again, we can just use the coefficients here. We just have to figure out where we're putting each thing. So we want to cancel out moles NO. So we want moles NO on the bottom here then. Our target is moles of NO3. Sorry, I keep saying NO3. Moles of O3. And then we just go back to the equation, look at the coefficients. Well, there's 1 mole of O3 for every 3 moles of NO. 3 times the third is just equal to 1. So we find 1 mole of O3. Any questions about where I'm pulling these numbers from, or how are we feeling about molar ratios? Not so bad? Thanks for some indication, Charlie. I appreciate it. Yeah, okay, good. All right. So in our balanced equation, we can see that there are coefficients that represent a ratio of molecules. So we can compare molecules to molecules as well as moles. We can also do moles to moles. Did we talk about grams at all here? No, because you can't use coefficients as a ratio of mass, so don't do that. Let's start the next one here. So the coefficients are a little bit more complicated, but the process is just as simple here. So it's asking how many moles of water can be produced if we have 50 moles of oxygen gas being consumed. Again, we're just doing moles to moles. So if we start with what we know, well, we are told that we are consuming 50 moles of oxygen gas. Oxygen gas is O2. Then we multiply by our conversion fraction. And so if we are trying to figure out moles of water, that's our target, and target goes on top of the fraction. Moles of H2O. We also want to cancel out O2. So moles of O2 will be on the bottom. And then here, if we look and find our coefficients, O2 has a coefficient of 25 and H2O has a coefficient of 18. So we have 18 moles of H2O for every 25 moles of O2. You do that calculation, you'll get that we have 36 moles water. Correct. All right. Start with what we know. Well, reading this question, I see that we are burning 8 moles of octane. 8 is the only value given to us. That must be what we start with. If we have 8 moles of octane, which octane is the C8H18. Label that for you guys there. So if we start with 8 moles of octane, it's asking how much CO2 will we produce? Well, here we're going moles to moles, so we're just using those molar ratios again. We want to cancel out octane. So we put mole C8H18 on the bottom. Our target is carbon dioxide. Does anyone remember the formula for carbon dioxide? I almost just said it. CO2, awesome. So we want to put that on the top because that's our target. And then if we fill in coefficients here, octane has a number of what? 2. What about CO2? Great. 8 times 8 is 64 moles of CO2. All right. Let's say we start with 14 moles of octane. So if we have 14 moles of C8H18, how much oxygen gas did we use? Well, we want to cancel out octane, so we put that on the bottom of our fraction here. And we want to know oxygen gas, which is O2. So that's what gets put at the top. And so we just have to decide what values to put in there. O2 has a coefficient of 25. According to the formula, octane gets a 2. And so if we multiply this out, you get 175 moles of O2. Are there any questions on these problems so far? Still feeling fine? Okay, good. All right, last 2 here. Now this one's asking, how many moles of aluminum sulfate could be formed from 0.442 moles of aluminum chloride? So we have to remember what these things are. So looking at our equation here, aluminum chloride is this reactant. And then this product is aluminum sulfate. So for this one here, it's wondering if we start with 0.442 moles of aluminum chloride. So that's why I'm going to start my conversion. All right, so that's how many moles I have of it. How many moles of aluminum sulfate am I making? So I set up my conversion fraction. I'm going to put moles of aluminum chloride on the bottom and moles of aluminum sulfate on the top. What is the coefficient that goes with aluminum sulfate? 1. That goes on the top. Then for aluminum chloride, it gets a 2. So we're just halving this number and you would get 0.221. Sorry. 0.221 moles of aluminum sulfate. What number do I start the next one with? Wonderful. Start with what we know. Well, we have 6 moles of aluminum chloride. Set up our conversion. We want to cancel out aluminum chloride, so I'm putting that on the bottom. And our target here is moles of nickel sulfate. So we'll put mole and ISO4 on the top. What number goes on the top? 3. What about on the bottom? 2. 6 times 3/2 equals 9 moles nickel sulfate. Next one. If I have 9.3 moles of NiCl2. I need to figure out the molar ratio going from NiCl2 to aluminum sulfate. So I'm putting moles of nickel chloride on the bottom, moles of aluminum sulfate on the top. And then if I look at the balanced equation, aluminum sulfate doesn't have a coefficient, so that gets a 1. Nickel chloride has a 3. So there'll be a 3 on the bottom. So 9.3 times 1 divided by 3 is equal to 3.1 moles of Al2SO4. Any questions on that one? All right, just a couple more here. How many moles of carbon dioxide can be produced from 6.7 moles of methane? Who remembers what the formula for methane is? Woo! So we have 6.7 moles of CH4. And we want to know how many moles of carbon dioxide can be produced from this. So our target is CO2. So I'm putting carbon dioxide on the top. We want to get rid of methane. Methane goes on the bottom of our conversion fraction. And if we look at the molar ratio, CO2 has a coefficient of what? What about methane? What? So what's our answer? Awesome. So I want to do one of these because when problems get a little bit more crazy and we're doing more steps, you still have to show your work, even if it's 1 to 1 or the ratio is 2 to 2. You still have to show your work. It's starting to make sense why I got a little bit angry, or not angry, I should say stringent on the labeling rules, because now we're talking about more than one species. Now we're not just dealing with methane. Now we're talking about methane and carbon dioxide. So this is why I wanted you guys to start labeling with your species, because stoichiometry gets crazy. All right. Yeah. Yes, it would. Thank you. I wrote CH4 there. Should have said CO2. All right. Last one, last couple here. If we start with 0.50 moles of methane, how many moles of oxygen gas are needed? What am I putting on the bottom of the fraction? Awesome. And how many moles are there from the balanced equation? Okay, now what goes on top? Perfect. 2 moles of O2. A half times 2 equals 1 mole O2. C says, stop and think. What does 1 mole of O2 weigh? 32. So 1 mole of O2 is just the molar mass of O2. Well, it's O2 though, so 16 times 2. So 32 grams. So don't forget that molar mass is just the definition of how many grams 1 mole of that substance weighs. Okay.